Hi, this is Sally's Book Talk. Tune in daily for global bestsellers car-suited just for you. Hello, dear Sally listeners. I'm Sally, host of Science with Stories. I'm also the author of The Shape of Time, a China Popular Science Book Award winning work. Today, I'll present an intriguing science book called The Flexible Universe. This is the debut work from my buddy Musk, host of Himalaya's popular show, History of Science Cunny. With over 100,000 followers now, understanding the author is the best shortcut to appreciate any work. So let me first introduce this extraordinary person. I met Musk at University of Shanghai for Science and Technology campus in 1996. I was a freshman while he was a senior. We've been colleagues for 20 years since my graduation. Friends call him Brother Ping, even those older than him. This nickname actually reflects our camaraderie. Many see Brother Ping as eccentric, single past 40, always immersed in his passions. But I know it's not eccentricity, but determination beyond most people's. He perfects whatever he pursues. Over a decade ago in our band, he played harmonica obsessively while I played classical guitar. He practiced harmonica unabashedly in cafeteria lines, ignoring all stares. For 6 months straight, he ate cured meat noodles daily until the restaurant closed. Several restaurants met similar fate. Brother Ping summarized brilliantly. Any restaurant that's uncrowded, tasty, and affordable will close within half a year. He only drinks Pepsi. Never changed since college. When asked if he prefers Pepsi's taste, he admitted no difference, but sticks to Pepsi regardless. For 3 years in Pudong, he'd walk to a newsstand each morning where the owner already placed reference news waiting. These two never exchanged a single word. He's lived in the same rented room for 10 years, won't move unless evicted. His Himalaya show has maintained strict Sunday midnight updates for 3 years straight. Brother Ping loves analyzing things. Fresh out of college, we frequented a stir-fried noodle stall. When they started offering free fried eggs, he predicted it would trigger an economic ripple effect on the whole street. He could deduce economic principles from office workers' takeout choices. Brother Ping often says all things are universally connected. His professional skill, a graphic designer who codes, or former senior human-machine interaction designer. A military enthusiast who buys every issue of military magazines and argues on forums. Also an astronomy buff who built his own telescope to photograph moons and galaxies. His childhood love for crosstalk shows makes his science history narration incredibly engaging. On Himalaya, his show ranks alongside comedy giants like Guo Gang in the crosstalk category. The Flexible Universe is the physical book version of his free album, The Big Bang, subtitled A Spin-Off of Relativity. It explores relativity's birth and its Yension theories. This crosstalk style science history uses official sources, but makes them as lively as the Ming Dynasty stories. While discussing science history, it naturally incorporates numerous scientific concepts. Brother Ping masters scientific explanations, pinpointing core concepts with remarkable clarity. His historical approach shows scientific discoveries don't emerge in isolation, like thermodynamics developing alongside steam engine applications. Electromagnetism became inseparable from the Second Industrial Revolution's electrical revolution. His second perspective reveals scientists as complex humans with emotions and interpersonal dynamics. Where there are people, there's drama.
Would you believe Einstein frequently skipped classes and had a shotgun marriage?
During WWII, scientists face moral dilemmas: national loyalty versus universal ethics. Different choices revealed their multifaceted humanity. My book, The Shape of Time, focuses on relativity's knowledge itself, with scientists as supporting cast. Natural laws always take center stage in my works. Brother Ping's narrative makes scientists the protagonists of their human stories. Though separated by eras, I feel traveling through time with these scientific masters. He often marvels. Why study science history? Brother Ping sees it as humanity's cognitive journey. Solving old problems only reveals new ones, like detective work requiring patience and insight, he summarizes. Human progress resembles an endless expedition. Studying history is like reviewing our footprints. We realize we've taken many detours, yet marvel at how far we've come, knowing the road ahead remains long. What paths have we traveled on relativity's journey? What roads lie ahead in our visible future? This is what the flexible universe attempts to reveal. Relativity's development history is full of fascinating stories. Let me first outline the book's structure, then highlight key points. Relativity developed in two phases: special relativity, then general relativity, both pioneered by Einstein. But relativity didn't emerge from nowhere. It was scientific evolution's inevitable product. Pre-relativity electromagnetic research laid foundational pilings through collective scientific effort. General relativity appears as Einstein's solo triumph, but actually built on mathematicians' cumulative knowledge, like constructing buildings. Scientific progress requires brick by brick accumulation. Generations of scientists pass the baton in this endless relay race. Modern cosmology and astronomy fundamentally rest on general relativity's framework. Einstein laid the cornerstone for contemporary cosmology. As Brother Ping says, cutting edge. Cosmic phenomena like black holes and dark energy are relativity's brainchildren. Let me guide you through this journey's highlights in broad strokes.
Special relativity revolutionized our understanding of time.
Newtonian physics viewed time as absolute, and unchanging time flows uniformly, like a river, as Confucius said. While this aligns with human intuition, science proves intuition often deceives. Light speed became the pivotal concept in establishing special relativity.
The pursuit of light speed ultimately overturned absolute spacetime concepts, revealing time's intrinsic link with light velocity.
None of the researchers anticipated this revolutionary outcome.
Galileo pioneered experimental methodology by attempting to measure light speed, replacing philosophical speculation with empirical verification.
His experimental approach established science's fundamental principle: let facts speak through designed experiments.
Galileo's groundbreaking hypothesis about light's finite speed was remarkable. but his experimental attempt truly revolutionized scientific practice.
Limited by 17th century technology, his measurement failed but ignited humanity's relentless pursuit. Danish astronomer Irmer first demonstrated light's finite speed through Jupiter's moon observations. After Irmer, British astronomer Bradley discovered stellar aberration, refining light speed calculation.
French physicist Fizeau achieved laboratory measurement using rotating gears, achieving mere 5% error from modern values.
Maxwell ultimately revealed light's essence as electromagnetic waves through his revolutionary equations. His dynamical theory of the electromagnetic field established light as electromagnetic disturbances propagating through fields. Maxwell's equations became the architectural framework for electromagnetism, considered physics' most elegant formulas. Scientific revolutions culminate when phenomena are mathematically unified, as seen in Newtonian mechanics and Einstein's relativity. Theoretical breakthroughs inevitably drive technological leaps. All modern electronics stem from Maxwell's electromagnetism and quantum mechanics. In 1879, Edison illuminated the light bulb, marking humanity's entry into the electricals age. That same year witnessed Einstein's birth, the central figure of this book. Brother Ping has thoroughly studied Einstein's complete works, mastering every detail of his life. His narration presents Einstein not as textbook icon, but as flesh and blood human with passions and flaws. At 1900's turn, while global tensions simmered, young Einstein's main concern was unemployment in Zurich. He became homeless wanderer. 4 no's: no job, no home, no money, and no girlfriend. Surviving on Italian relatives, remittances, he desperately sought academic positions with no responses. His salvation came from classmate Grossmann, whose well-connected father learned about Swiss patent office vacancies. The office advertised for mechanical engineering graduates with physics background, essentially a tailor-made job listing. This hiring strategy reflected the electricals age's demand for interchio expertise. Patent offices needed professionals who could evaluate increasingly complex electrical inventions. Brother Ping's vivid historical reconstruction shows Einstein as multidimensional character, not idealized genius. As Bill Bryson wrote in A Short History of Nearly Things, God knows the facts, but not this particular narration. That's why I enjoy reading different authors' perspectives on the same historical events. Brother Ping's historical narratives stand out for their vividness.
1905 marked Einstein's breakthrough year at the patent office, producing 6 landmark physics papers, or 5 considering one was supplementary.
This scientific milestone became known as Physics Miracle Year, leading to 2005 being designated World Year of Physics.
Special relativity fundamentally transformed our understanding of time as relative rather than absolute.
Time dilation means astronauts' clocks slow down relative to Earth observers. This is the famous time slowing and length contraction effect. Crucially, relativity isn't philosophical speculation, but mathematically rigorous theory with testable predictions. Its falsifiability distinguishes it from pseudoscience, a cornerstone of scientific validity. Initially met with skepticism, relativity gained support from physicists like Planck, despite lacking experimental confirmation.
The famous twin paradox exemplifies relativity's counterintuitive nature. Chapter 8 explores this classic thought experiment.
If one twin travels at near light speed which sibling ages slower. The apparent symmetry breaks when considering acceleration. French physicist Paul Langevin first proposed this paradox in 1911, highlighting relativity's philosophical implications. The original twin paradox concept didn't involve rockets. Langevin's 1911 version used different hypothetical scenarios. While most explanations require general relativity, special relativity alone suffices with proper space-time analysis. Brother Ping employs Minkowski diagrams to resolve the paradox without invoking general relativity, a rigorous yet accessible approach. All valid explanations converge on the same conclusion: the traveling twin ages less. This paradox naturally bridges to general relativity's broader framework.
Despite similar names, special and general relativity differ fundamentally. One word marking a cosmic leap.
Special relativity applies only to inertial frames, idealized references absent in reality. General relativity discards inertial frames, creating universal equations at the cost of complexity. Mastering general relativity requires years of specialized study even for physics majors. Special relativity links time-spats and motion. General relativity adds gravity into this union.
Four fundamental elements unite in Einstein's field equations. Mathematics describing cosmic fabric. The book's title, The Flexible Universe, perfectly captures spacetime's malleable nature per general relativity. General relativity reveals spacetime as pliable fabric rather than rigid stage, a revolutionary conception.
General relativity's most profound implications all concern cosmological phenomena, hence the apt title, The Flexible Universe. Let's examine its major predictions, starting with the Big Bang theory.
Einstein initially struggled with his equations, finding they predicted dynamic expansion, contraction, rather than his preferred static universe.
He introduced the cosmological constant to force static solutions, what he later called my greatest blunder. Soviet scientist Friedman derived expanding universe solutions without this constant, but Einstein rejected his paper. Belgian priest Lemaitre reached similar conclusions, earning Einstein's dismissive "good math, bad physics" remark.
Robertson and Walker synthesized these ideas into the FLRW metric. Foundational to modern cosmology.
What's a metric? It's the rule of measurement, a mathematical framework describing space-time's evolving structure.
The FLRW metric revealed a stunning conclusion. The universe began as a singularity expanding over eons into its current form. Einstein initially rejected these findings, but was proven wrong when Edwin Hubble observed galaxies fleeing faster the farther they were.
Hubble's 1929 observations forced Einstein to retract his cosmological constant, demonstrating scientific integrity.
In 1948, Gamow proposed the primordial fireball theory, later mockingly called Big Bang by studying proponents. Despite initial skepticism, cosmic microwave, background, radiation detection validated Gamow's predictions.
The Big Bang model now stands firm with mathematical rigor and observational evidence.
Another relativity egg, black holes. The first theoretical model was Schwarzschild's solution to Einstein's equations.
Schwarzschild's solution showed any object collapsing beyond critical radius becomes light trapping, later termed black hole by Wheeler.
While Schwarzschild holes dominate pop science. Variants exist like RN black holes with dual event horizons enclosing normal spacetime. The 1960s revealed Kerr black holes, rotating oblate spheroids with equatorial bulges, unlike static Schwarzschild models.
Kerr's geometry features ergospheres where spacetime itself rotates, allowing energy extraction via the Penrose process. Approaching the infinite redshift surface, observers see you fade as light wavelengths stretch beyond detection.
Theoretical physicists calculate that losing mass into the ergosphere could slingshot your ship outward faster than entry speed.
These aren't sci-fi fantasies, but rigorous mathematical predictions from Einstein's equations. Thus, Kerr black holes make perfect material for sci-fi creations. The iconic film Interstellar featured precisely this black hole model familiar to global audiences. Stephen Hawking, the renowned British physicist, achieved fame through black hole research.
Though universally recognized, few realize Hawking specialized in black hole physics.
His groundbreaking Hawking radiation theory reveals two revolutionary insights.
First, black holes aren't completely black, they emit particles. Second, black holes gradually evaporate rather than being eternal. Relativity scholars celebrated this discovery, while quantum physicists faced existential crises.
Why Hawking radiation violated fundamental conservation laws like baryon number and information preservation. The collapse of information conservation threatened quantum mechanics' unitarity principle, where probability totals must equal 1.
Imagine flipping coins where heads plus tails probability not equal 1 like magic tricks defying physics.
Previous assumptions suggested information might survive inside black holes, but Hawking's evaporation theory erased it completely. Black hole radiation, being pure thermal emission, carries zero information akin to burning secret messages permanently. This contradicted quantum theory's core tenet: information can be scrambled but never destroyed.
The crisis persisted until Gerard 't Hooft and Leonard Susskind rescued information conservation through holographic principal theories.
They discovered that a photon escaping a black hole reduces its mass by a tiny bit. The black hole's radius shrinks slightly, causing a minuscule shift in its black body spectrum. This spectral shift encodes escaped information through Hawking radiation.
Everyone was stunned. Who knew tracking single photons mattered?
Even stellar mass black holes weigh millions of suns, yet we account for individual photons. How can you even consider accounting for one photon in such massive systems? Most dismiss this photon level change as negligible. But 't Hooft insisted every photon must be counted. Quantum mechanics demands precision. Each escaped photon reduces mass, shrinks, radius, shifts spectrum, information escapes through these quantum effects. What sounds simple requires calculating quantum tunneling effects. Mathematically intensive work. Their calculations on Schwarzschild and IRN black holes earned 't Hooft the International Gravity Research Prize. Countless fascinating black hole phenomena exist beyond these examples. Crucially, all black hole types emerge from mathematical rigor, not philosophical speculation. These equations originate from Einstein's field equations, the holy grail of general relativity. From supernovae to dark matter, modern cosmology rests on relativity's mathematical foundation. Whether studying neutron stars or dark energy, Einstein's 1915 theory remains indispensable. The 2016 gravitational wave detection confirmed another relativity prediction. Reading The Flexible Universe offers two key rewards.
First, intimate encounters with scientific legends as real people.
We become time-traveling observers, witnessing history's greatest scientific moments.
Second, absorbing complex physics through engaging storytelling and humor. This book chronicles a 200-year physics journey that reshapes worldviews and expands imaginations.
Readers embark on an intellectually fulfilling adventure through these pages. No summary can capture Brother Ping's unique narrative charm. Better experience it firsthand. Let's begin with geometry, specifically Euclid's system, familiar to most modern readers.
When Ming scholars Nu Guangqi encountered Jesuit Matteo Ricci, their collaboration birthed China's first geometric translations.
Why did Snu obsess over this work? Its axiomatic system built logical structures unknown in Chinese mathematics.
Hundreds of theorems derive from 5 postulates, revolutionary systematic thinking for 17th century China.
This axiomatic foundation created rigorous mathematical frameworks essential for scientific progress.
Even Emperor Kangxi studied Euclidean geometry. His homework preserved alongside triangular models.
The emperor's math skills reportedly reached modern high school level, though less practiced.
He famously focused surveying skills, calculating distances that left ministers awestruck.
Euclidean geometry begins with 5 postulates, the fifth being particularly tricky. The convoluted fifth postulate states, if two lines intersect, a third making interior angles less than 180 degrees, they'll eventually meet on that side. Later simplified as, through any point outside a line, only one parallel line can be drawn. The parallel postulate. These postulates form geometry's foundation, accepted without proof, as self-evident truths. Euclid's system perfectly matched practical measurements for millennia. The problematic fifth postulate bothered mathematicians. It felt more like a theorem needing proof. Unlike other concise postulates, this one was wordy and only used after 29 propositions. For centuries, mathematicians tried eliminating or proving it from other postulates.
This pursuit ultimately led to non-Euclidean geometries, but that's another story.
For more fascinating history, follow History of Science Company. I'm Brother Nuo, Wu Yingting, Wang Ji, News Dong. We're the voice of science.
That concludes our book breakdown. Find keynotes below. See you tomorrow.